Happy Tuesday, I guess. It's spring though, officially, so that's pretty good. All right, so you got your quizzes back. I don't post solutions because then it forces me to make notes on your quizzes to kind of correct you. If there are any marks taken off that you're sure why, or if you want to just kind of go through the quiz, I'm happy to do that, any of the quizzes. But just use it and study for the final exam. You'll see it all again. You'll have another shot and it'll be fine. Yeah. Yeah, it was a little bit lower than the other two quizzes, which was kind of surprising to me, but I know it's a busy time too. So I just, yeah. And like I have been saying all along, right? If you do better on the final exam, I'll just pretend you weren't here and put the weight on the final exam, right? So it's really no harm, no foul, right? But it's better to write the quiz than to not write the quiz, is always the case. All right. Are you guys ready for a new chapter? Chapter 7. It's our second to last chapter. Well, that's not entirely true, I guess. We kind of duck into chapter 9, depending on how much time we have, we kind of do a little peekaboo, but not really. So chapter 7 is inference for numerical data. Okay. Inference is a word that we've seen before, right? Inference just means really it's just an umbrella term for confidence intervals and hypothesis testing. Okay. We have been doing inference for categorical data, right? Proportions are categorical data. Now for numerical data, what we're going to have is we're going to analyze the means. So the mean, which is the average, right? At the beginning of the term, we said, let me just go close this because I feel like I talk loud. Not as loud as Joya, but pretty loud. Just on the off chance that she's in the hallway listening. So at the beginning of the term, we said, okay, well, if I have numerical data, then I should be able to talk about the mean, and we can talk about the mean distance, the mean time, the mean height, that kind of thing, right? So these are all numerical measurements. Okay? And that's why we spend so much time at the beginning of the term. Maybe it didn't feel like so much time, but for me, it felt like so much time talking about, okay, well, what type of variable is this, right? Because we need that, that core knowledge, right? A categorical variable, okay, I'm going to do a z-test for proportions, for example, or I'm allowed to do a chi-squared. Those are options that we've seen, right? Now for numerical data, we're going to have other options, different options, okay? And so that's what we're going to learn about in chapter 7. So I just want to say kind of versus, that was a weird B, versus chapter 6, which was inference categorical data. Maybe I'll capitalize just like I did above. Categorical data, right? Which meant proportions. And then I'm skipping these because they don't apply to us. All right. If you had to venture a guess, where do we start? How about with one sample mean questions, right? We started with one sample proportion questions, then we moved into 2 sample proportions, right? If I want to compare the 2, okay, now what if I have more than 2 proportions? Then I use a chi-squared. We're going to do the exact same thing for means. We start with one mean, comparing it to some value, right? And then we have 2 means. I want to compare the means from 2 different groups. And then, well, what if I have more than 2 means? Then I do what's called an ANOVA, which we'll get you, right? And so we're going to progress the same way. And what's really, really nice is you get to flex your hypothesis testing and confidence interval muscles again, which are just getting stronger, right? And so by the end of chapter 7, hopefully you'll just be kind of bored with hypothesis testing, confidence intervals. Yeah, I get it. And that's my goal, I guess. To bore you? No. To learn you. So 7.1 is on one sample means with the t distribution. So in terms of the type of question, I'll just call it one sample mean, right? And I'm going to do that on quiz 4 again, where you have to tell me what type of question it is, because it is so important that you're able to identify them. Because once you've identified what type of question you have, then you have also identified which part of the formula sheet you're kind of stuck on, and it just kind of simplifies things. Okay? I think you're going to like it here. T-tests are pretty common things that we do. And if you want to sound like you know what you're doing, you can always suggest in a group setting, well, couldn't we do a t-test? And it's rarely like a bad suggestion, as long as you make sure you have a numerical variable, obviously. But if you're talking about averages, couldn't we just do a t-test? And I was like, yeah, that's pretty good, I guess. Yeah, let's try it. And then there's more kind of advanced things that you can do, but they're very, very common. Okay, so t-tests is what we're going to be doing. All right, so in terms of the type of question, it's a one sample mean question. Okay. What gets a little bit confusing is that we introduce this t distribution, which is where the t-test comes from. Okay, it's very similar to the z distribution, so the normal distribution. Okay, so it's very similar to the normal distribution, and I'll capitalize it just to emphasize that it's a name again. So the normal distribution, or the z distribution, if you prefer, which is what we've been working with, right? It has this similar shape. Okay? It's centered on the mean, and it's going to have some standard error, just as before. Okay. The thing is, just like the chi-squared distribution, the shape of the t distribution is going to change with the degrees of freedom. Okay. And so I'll write that down. Just as the chi-squared distribution changes with the degrees of freedom, the t distribution also changes. With the degrees of freedom. Not as dramatically as the chi-squared, right? The chi-squared went from super, super skewed to the right to approximately normal as you kind of increased your degrees of freedom. But here we're just going to start at a normal looking distribution, and there's a little blurb that an image that I want to grab. This one. Just to show you that it really, really doesn't look that different from what we're used to. Okay. So just as a note, the normal is the Z distribution. Okay. Kind of tricky because it gets lighter and lighter, but they're all kind of grayish looking on here, but it's in the textbook as well. Okay, so what happens is the normal distribution is the kind of the darkest line. Okay, and if I were to describe it compared to the other lines, right, they look very similar, similar shape, similar-ish spread. Okay, but what happens with the Z distribution or the normal distribution is it's very tight on the axes, right? And so, and then it kind of smooshes, that's the technical term, smooshes, no, it's not, smooshes up, right? And so, right, there's not a lot of room in the tails. We know from before that the tails, there's room in the tails to infinity and negative infinity, right? So there's always a probability, okay? And just as before, the area under the curve is still 1, right? So if we're smushed down on the axes, and I like to use my kind of right? And so if you kind of smush down on the axes like this, then you've got a high peak, right? If you kind of open your elbows, you guys are missing something if you're joining on Zoom. If you kind of open your elbows, can't describe it, it's a chicken dance, then the peak kind of pushes down, right? So the total area is still 1, right? And so what happens is as you increase your degrees of freedom, okay, so then your tails are going to get closer and closer to the axes, right? So if you have 1 degree of freedom, I haven't told you how to find it, I'm holding out on purpose. I won't be able to hold it much longer though. For 1 degree of freedom, okay, then you've got this very kind of open tail distribution, I guess, right? Because that's going to be this upper line here. What does a lot of area in the tail mean in terms of probabilities? It means that the probability is larger of seeing these extreme values. Okay, the reason for that, now I'm about to tell you, is that the degrees of freedom is going to be n-1. So it's your sample size minus 1. Okay. This is for a 1 sample mean question, which is where we're starting. Okay. So it's your sample size minus 1. What does a sample, a degree of freedom of 1 means you have a sample size of 2, right? We intuitively, we know can't really draw any huge conclusions about those 2, right? You'd need to increase your sample size. So how is that reflected? Well, it's reflected in having a huge area in the tails, right? Well, these 2 that I saw are hovering around here in the center, but I mean, there's still a high probability of seeing values out in the tails, right? Because I have a very small sample size. Luckily, even at 8 degrees of freedom, which would mean a sample size of 9, right? 9 minus 1 is 8. That distribution looks a lot like the Z distribution, right? So it doesn't take a whole lot to get our T distribution to kind of look like the Z distribution, okay? But we do need the degrees of freedom because it's going to change just ever so slightly. Okay. Okay. So let's kind of, how do I summarize what we just said? The degrees of freedom, should have just written DF, but it's too late now, determines the shape of the distribution. As the degrees of freedom increases, which is another way of saying as the sample size increases, right? N increases because of their relationship, the T distribution approaches the Z distribution. The T distribution approaches the Z distribution. For small degrees of freedom, right? So here's kind of first bullet point, second bullet point. For small degrees of freedom, the area in the tails is thicker. Can I say that? The tails are thicker. Let's say that. The tails are thicker. Okay. Which means what in terms of the probability? It means the probability of extreme values is higher. Okay. Which means the probability of extreme values is higher, right? Because the area under the curve and in the tails is the probability of seeing something as extreme or more extreme, right? So if you have more area in the tails, then the probability of seeing some kind of extreme is higher. Okay. So that brings me to the central limit theorem, and I'm gonna just make a little note here and erase it. Feel like I jumped around maybe. We saw the central limit theorem for proportions, and it exists, of course, for means as well. Okay, so this is just going to be how we identify the mean and the spread of this distribution. Just like before when we've kind of parking lotted normal distributions in terms of means and standard deviations for a little bit, right? We went to chi-squared, but the normal distribution, right, and the T distribution, we need to know the center and the spread, and then we'll kind of know what this thing looks like, okay? And so the central limit theorem, CLT, helps us do that. So when we collect a sufficiently large sample of n independent observations, okay, so this is going to translate into our conditions, okay, but we're going to talk about that more, conditions, right? So we have to have a sufficiently large sample of n independent observations. So independence is still a condition. It's always a condition. So we'll get into that, but for now, we'll just leave it there. From a population with mean mu and standard deviation sigma, the sampling distribution of X bar will be nearly normal with a mean of mu, so it's centered on the population mean, and a standard error of sigma over root n. And just as a reminder, it's going to come up a lot today. So X bar, remember, is the sample mean. Which means that if I want to hypothesize about one sample, so sorry, not one sample, one proportion, oh my gosh, words, population, scratch that, scratch that, scratch that. One population mean, what's my point estimate, right? So for inference, for one population mean, really important I don't screw that up again. We need a point estimate. Again, good point estimate for the population mean, which is mu, right? I'm trying to learn about mu. Well, my point estimate is, of course, going to be X bar, my sample mean. It's my best guess. It's all I've got. All right. And if the conditions are satisfied, I'm allowed to assume that that looks roughly like my population mean. And then the standard error of the point estimate, is going to be sigma over root n. What's a huge problem that we have here? It's been a while, so I don't actually expect you to. The problem is sigma, right? Sigma is from the population. It's the population standard deviation. So what does that mean? We had the entire population, we calculated the standard deviation, and then we tossed them all back and said, forget this, let's try to figure out what the mean is. I'll just take a sample, thanks. Makes no sense, right? And so we're not going to do that. And we've done similar things with the proportion, right? We said, well, I don't know the population proportion, so I'm going to use the sample proportion, right? And so we use S, which is the sample standard deviation instead. So therefore, the standard error of X bar is going to be S over root n. As a quick introduction to degrees of freedom and where it came from. So why do we have the T distribution? It's because, well, I'm estimating X bar, but I'm also estimating S, right? So there's variability in X bar. If I took a new sample, a different sample, I would get a different X bar, right? So there's a distribution of X bars, but that's assuming that the standard deviation is held steady, but that's not the case, right? The standard deviation would also have variability. And so that's why we're at the T distribution instead of the Z distribution. That's not important, right? Just remember that you're using the T now instead of Z. It is important, but not for us. Shouldn't say that it's not important. It is, but not for us, okay? And so I kind of think of it as, okay, the T distribution is handling, you know, when you have to like pat your head and rub your stomach. So it's like X bar is changing and S is changing as you collect different samples in theory, right? And so that's where the T distribution comes from. Okay. What we can write then is the sampling distribution of X bar is approximately normal with a mean mu and a standard deviation sigma over root n. Okay. We're going to center this on the hypothesized mean. Okay. We center the distribution on the hypothesized mean. Which is what we did before, but I don't know if I said it like that, so that's okay. Okay, so what are the conditions? What's really nice is the conditions are the same for a confidence interval or a hypothesis testing question, right? So it's a lot simpler than proportion questions. So we said, okay, when we collect a sufficiently large sample, okay, so it has to be sufficiently large, so we'll deal with that, of n independent observations. So of course, the first condition is independence, and then the second condition is this sufficiently large. And there's a, here's the one I want. Oops. I actually want this whole thing. Spoiler alert. We use a sample size of 30 as a guide, right? Sufficiently large usually means larger than 30 as a threshold. I've seen reports with as low as 10. Okay, so it's pretty flexible, but 30, you're absolutely safe. Yeah. So depending on what field you're in, social sciences, right, they don't get very many responses, surveys and things like that. And so then you'd have to kind of lower it in order to be able to use the t-test. Right. So here are the two conditions. First one is independence. Okay, the sample observations must be independent. Why is this capitalized? The most common way to satisfy this condition is when the sample is a simple random sample from the population. We've seen that before, right? We've argued that before. I collected this sample randomly, so I may assume that the observations are independent of each other. Okay. If the data come from a random process and analogous to rolling a die, this would also satisfy the independence condition. Okay. And so here, when it's a simple random sample from the population, you can assume independence. Then we have what we call the normality condition. And if you had a look at the solutions to the practice quiz that I posted, quiz 3, I called the success failure the normality condition. We didn't call it that in class. We called it the success failure as kind of a mental nudge to what to do. Okay? But it is the normality condition as well. Okay? And it's checking the sample size still, okay, but in a different way, sort of. So when a sample size is small, okay, so we're allowed to do a t-test with small sample sizes, but then we also require that the sample observations come from a normally distributed population. Okay? So then things like heights, weights, distances, all that kind of fun stuff, a lot of those things come from a normal distribution. So then we can deal with small sample sizes and it's totally fine. We can relax this condition more and more for larger and larger sample sizes. Okay? So if you have a large sample size, what does that mean? It means that you're allowed to analyze the mean from a skewed population, right? Skewed populations are things like anything to do with money, right? Lots of businesses earn small amounts of money, very few earn large amounts of money, right? That kind of thing. And so, so as soon as it has to do with money, then you have a skewed distribution. But if you increase your sample size, right? So it's large enough, let's say you hit 100 or 1,000, right? Then even though you're pulling from a skewed distribution, you're still allowed to analyze the mean. Yeah. So that's kind of cool and groundbreaking. So, oh, sounded like it was in here. Okay, so this condition is obviously vague. They even say it in the textbook, making it difficult to evaluate. Okay, so here are just a couple of rules of thumb. And like I said, it depends on what field you're heading into, what kind of the rule of thumb is, but 30 is absolutely safe. So there's no perfect way to check the normality condition. So we're going to use 30 as our guide. Okay. So if your sample size is less than 30, what you have to do is you have to look at the distribution and just make sure there are no huge outliers, right? So it doesn't have to look approximately normal even, you just can't have any outliers, especially if you have a sample size of 8. If you look at a histogram of 8 things, it's not really gonna look like anything, right? It's just going to be a couple of bars, maybe approximately normal, maybe not. So our thing here is, so if the sample size is less than 30 and there are no clear outliers in the data, then we typically assume the data come from a nearly normal distribution to satisfy the condition. Okay. So you have to be able to check for outliers, right? We developed kind of strict rules for outliers. We use the 1.5 IQR rule to figure out if we have outliers. You don't even have to take it that far, right? And I'll kind of, let's see here. We know how to two words, not one, how to check for outliers. Right, the first one is the 1.5 IQR rule, right? It's a little bit extreme, you don't need to use it. Don't need anything this extreme. But I'm just telling you that you know how to do it, right? What's another one? You can just eyeball it, right? You can, if you are able to make a histogram, then you can look for outliers. Yeah.
When you say like extreme, you just mean kind of like
overkill.
Yeah. Something a little like eyeballing it.
Yeah. So it's just a rough guide. I mean, even if you're eyeballing the data set and things are kind of 3, 5, 7, and then all of a sudden you have a 300, that's bad, right? Can't handle that. Okay. And so you can just make a histogram. Okay. Kind of middle of the road between kind of the strict 1.5 IQR rule and just making a histogram and eyeballing it, right? So eyeball it is, you look at the minimum and maximum, right? Obviously, there are no data points beyond those two things. So if the minimum and the maximum are within 2 or 3 standard deviations of the mean, then you're safe, right? And so if you're given the minimum and the maximum, check to see if they are within 2 or 3 even. I would push it to 3, depending on how desperate you are, right? 2 is good, 3 is fine. 2 or 3 standard deviations of the mean. If the min and max are within this range, right, we can assume there are no outliers. We can assume no outliers. Last tool I want to give you, just so you have options, right? Depending on what information you have. If you have the mean and the median, if they're close to each other, right? What does that mean? It means it's approximately normal, right? Or at least symmetric about the mean, right? And so then you can also assume that there are no outliers, right? And so here, if, and this is only if you're given these things, right? It depends on what you have. If you're given a histogram, you can just look at it, right? If you have the minimum and the maximum, the mean and the standard deviations, then you can do these calculations, right? And so given the mean and median, if they are close to each other, they don't have to be exactly equal, but kind of relatively close to each other. And I know that's hard, right? That's going to take practice. What's close, right? Maybe you prefer to just check the minimum and the maximum kind of for hard, hard data. Given the mean and the median, if they are close to each other, we may assume there are no outliers. So that's nice. That's only if the sample size is less than 30. Then you have to argue that, okay, there are no outliers, so it's safe. The normality condition is satisfied. If, and I'll just scroll up, but I'll scroll down again. If the sample size is at least 30, and there are no particularly extreme outliers, so it still can't handle extreme outliers, then we can assume that the sampling distribution is nearly normal, right? Even if the underlying distribution of individual observations is not. So that's kind of cool. You can pull from a skewed distribution, and as long as you pull enough data, you can still analyze the mean. So pretty neat, right? So in terms of your conditions, right? If you have randomly sampled your data, you can assume independence. Then you check your sample size. Is it more than 30? If it's more than 30, you can say, because my sample size is more than 30, the normality condition is satisfied, right? If it's less than 30, then you would argue, okay, there are no clear outliers, and you've got kind of a lot of options to choose from here, right? Depending on what information you have. Okay. So once these conditions are satisfied, X bar will follow a t distribution with n-1 degrees of freedom. Okay. Now the t distribution, we've already used the t tables. So for the quizzes, right, all you have are the tables. Of course, we should be using software, but it's hard with written questions. And so, right, so for the quizzes and the final exam, you'll have the t table. So that's where we're going to focus. But I'll do one of those little questions where I show you how to do it in R. And then if you want to, you can use that, but you don't have to. All right, so we've already seen the t table. That's the one that you have, and I forgot to bring extras if you needed another copy, but you can stop by my office. I've got plenty. So here's the t table, and now it's all starting to come together, right? The degrees of freedom are here, right, on the left-hand side. So what have we said so far? What we've said is, okay, as you increase your degrees of freedom, the t distribution approaches the z distribution, right? So at infinite degrees of freedom, you have a z. Okay, kind of weird, but that's how it works. So we've only been working with this Z line, but if you kind of glance up a line to 1,000 degrees of freedom, these values are pretty well the same, right? For some of these, they're exactly the same to decimal places, right? But relatively the same, right? There's not a huge change, okay? But it's important that we use the degrees of freedom for T's, just because for small degrees of freedom, it's going to make a difference. Okay? So we already know how this table works, right? And T again is symmetric about 0, so there's only positive values. And so if you have a negative T, which you'll calculate, then you take the absolute value, so you drop the negative, and then you can use the table, and we can still build confidence intervals, and we can do hypothesis testing, right, with these p-values down at the bottom. And so now we're just kind of using the rest of the table for T. Okay. All right, so let's see here. I'm gonna grab, let's see, how do I want to, do I have a, this one's fine. Okay. When we use the table, if you are choosing between some degrees of freedom, so let's say here, right, it goes by ones, so that's all fine up until you hit 30. And then it hits 30, jumps to 40, 50, 60, 80, 100, 1000. Okay. One thing that you want to keep in mind is the link to the sample size, right? And so it's really important that if you have 79 degrees of freedom, for example, right, it's going to be tempting to go to 80, right? But you're going to have to drop down to 60, because what does 80 do? 80 says you have a bigger sample size than you actually do, right? So you're better off safe and going down to 60 instead, right? So you're always going to drop it down to the closest line on the table. Okay. Even, and I can't explain why, but sometimes it's painful. Like if you have 900 degrees of freedom, you want to go to 1,000 so bad, but you have to go to 100. I can't explain it, but it feels painful. Does it change anything between these values? No, not really, right? And it just feels like a sacrifice. So I have a sample size of 901, and I could have just had a sample size of 201, 101. Feels like a waste, right? With software, it would make a difference, right? But for us on the table, I don't know why, but it kind of hurts. So here, let's see here. Let's make a note. When using the t-table, use the degrees of freedom if it exists, right? So sometimes I have people kind of misunderstand what I just said, and if they have 15 degrees of freedom, they go to 10 or something crazy like that. I don't want you to do that. But use the degrees of freedom line if it exists. Otherwise, round down to the closest degrees of freedom. And I'll even clarify here, otherwise you're assuming you have a larger sample size than you do. Or otherwise you are claiming, right? That's actually what you're doing. That's the problem. Are claiming to have a larger sample size than than you actually do. Or have, I guess.
Comparatively, each chapter that we've just done, we're getting a rounded, but not like a decimal round or a decimal number round up. in previous chapters.
So it depends on what you're talking about, right? So when you're solving for n, if you're solving for a sample size that you need, right, to satisfy some criteria, then you need to round up because otherwise you won't quite reach that criteria. But now for your degrees of freedom, although it's linked to your sample size, so I know it's confusing, right? But you just have to kind of put yourself in, okay, well, if I up my degrees of freedom, I'm actually claiming to have a larger sample than I actually do. So that's lying. Lies, Damn Lies and Statistics is a book, famous book. Anyways, so let's just have a look at just a quick example. 7.2 maybe. What proportion of the t distribution with 18 degrees of freedom falls below negative 2.10? So in terms of drawing what's going on, you can draw your drawing the same way that we did, right? It's still going to look like a normal distribution, so we don't really discriminate that way. It's still centered on 0. And what do we have? We have t equal to negative 2.10. Same setup as before, right? I can say, okay, so I want to find this falls below this value, right? That's the area that I want to find. I'm not going to be able to find it exactly. I'll need software for that, but that's okay. So since, and it's the exact same setup, the absolute value of t equal to negative 2.10 is between two values, right? And I kind of put that in the center. So now I guess I need to make another one. I had 18 degrees of freedom, copy. Maybe I'll do this. Kind of bring in a portion, cropped up. How about them apples? Make sure they line up, otherwise it's not very helpful. And this little portion here. Right. 18 degrees of freedom is what we were told is. So once you know your degrees of freedom, you're stuck on that line. Just like the chi-squared, the degrees of freedom doesn't change because your sample size is not going to change, right? So it stays the same. And so once you have your degrees of freedom, right, then you're stuck on this line. This line behaves the exact same way that the Z star line does, right? So now you're just kind of changing your focus to the 18 degrees of freedom line. And that's going to depend on the question, right? It's going to depend on your sample size, but At 18 degrees of freedom, you can build a 95% confidence interval. What, Emily? No, we can't. Yes, you can. Point estimate plus minus a critical value, 101, times the standard error of the point estimate, S over root n. So you already have the components. We're going to talk about it, obviously, but you already have all the components. Okay. And so now if we want to find the area in the tail, we're just looking at the area in one of the tails. And so I'm looking at the one-sided probability, or P, and so awfully close here. Negative 2.1 goes somewhere in between here, right? So it's between 1.734 and 2.101. Which means that the area in the tail is between 0.025 and 0.05. And I didn't, the tail area is between 0.025 and 0.05. Right, so here, and it looks the exact same, but just as a refresher, negative 1.734 has a tail area of 0.025, and negative 2.101, oops, too many ones, has a tail area, and I moved it out. It's a lot closer than that. All right, but it's got a tail area of 0.05. So that means that the proportion is a probability, right? And you can convert it to a percentage if you want, but the proportion of the t distribution with 18 degrees of freedom that falls below negative 2.10 is between 0.025 and 0.05. Nice.
Numbers supposed to be flipped on there, like 4 and 2.101.
Yeah, they are. I can always count on you guys. Negatives are hard for some of us, myself included. There. Thank you. This close to getting away with it too. All right. Good. So let's see here. I think that we're ready to have a look at the formula sheet, right? And just kind of get the lay of the land. What are we expecting to see on the formula sheet before we even look at it, right? We're expecting to see the sampling distribution. Hopefully I put it on there. I can't remember. I'm expecting to see a formula for the confidence interval and also some stuff for hypothesis testing, right? And it's really all you need to answer these questions. So let's see here. It's easy for me to say, I guess. So one sample mean is the type of question that we're working on, right? Which means what? We're just going to have one sample and we have the average of it, and I want to compare it to a value. And so the degrees of freedom, just because LaTeX is kind of funny sometimes, it got bumped down here, but don't forget it. Oh, good. I did put the sampling distribution on there. Okay. So let's start with the confidence interval, right? The confidence interval in general, any confidence interval is the point estimate plus minus a critical value times the standard error of the point estimate. The point estimate in this case is X bar plus minus. Now we don't have a Z anymore, so we have a T, right? Because it follows the T distribution, so it's a T star. But like I showed you, you already know how to find it. It depends on the degrees of freedom. So that's why there's a little subscript n-1 here. So it's a T with n-1 degrees of freedom. But I also have the degrees of freedom down here, right? Just as a reminder. Okay. But this n-1 is just the degrees of freedom. And then the standard error of X bar is S over root N. So from the question, you're going to need a sample mean, you're going to need the standard deviation, and you're going to need a sample size. Okay. If the sample mean isn't clue enough, right, to guide you whether it's a proportion question or a means question, right, then the standard deviation is really going to kind of tip you off, right? As soon as you see a standard deviation, then you know it's a means type of question, right? Because we haven't seen standard deviations for proportions, right? We calculated standard errors using the sample proportions, right? But as soon as you see standard deviation, you know it's a numerical data type question. Okay. Hypothesis testing for mu. We want to learn about the population mean. So our null and alternative hypotheses have to be about the population mean. And we've seen this before, right? Mu naught is just a placeholder for the value that I want to compare my mean to, right? Is the mean different from 5? Is the mean different from 2, right? That kind of thing. Is it less than 4, right? Depending on the question. Okay. And so here, I just want to make a note here where mu naught is a placeholder for the value we want to compare our sample mean to. We saw that with P naught, right? P is equal to P naught. Is P equal to 0.5? Is P equal to 0.44? All those kind of fun things. Okay. So mu naught, again, is just the placeholder for a number. Right. Then we're going to calculate a T, right? And T looks kind of similar to a Z. It's not that different. What are we doing? We're seeing how far is my sample mean from my hypothesized mean, taking into account the spread, right? That's the exact same thing that we were doing for proportions as well, right? For Zs. And so here, right, T is the point estimate minus the hypothesized proportion. Oh, I'm stuck on proportions, and that's going to get confusing. Hypothesized mean over the standard error of the point estimate. So same layout that we had for proportions, right? Point estimate minus how far, which value you want to compare it to, and then divide it by the spread. Okay. Whatever happened to, I had this kind kind of cute example. Well, I've got another cute example about piano players that I guess we'll do. A Rizzo's dolphin. I want exercise 7.11. Play the piano. I would say the hardest part is just kind of getting used to reading these questions and figuring out kind of the typical layout, but also how to identify that it's a one sample mean question, right? And so we talked about, okay, if you see standard deviation, right, then that should point you in the right direction. Okay, so let's see here. Georgiana claims that in a small city renowned for its music school, the average child takes, so here, that's kind of another kind of pointer, is that it'll mention the average or the mean, right? The average child takes less than 5 years of piano lessons. We have a random sample of 20 children from the city with a mean, okay, a mean of 4.6 years of piano lessons and a standard deviation of 2.2 years. Okay. And so when you're given the mean and the standard deviation, right, and it's only from one group, well, what type of question is that? It's one sample mean, right? And so, right, if we were talking about 14 out of those 20 students, right, said that they had taken piano lessons, right? What type of question is that? That's a one sample proportion type question, right? So it can change ever so slightly and then it changes the type of question. So here, the mean of 4.6 years of piano lessons, that's going to be your X bar is 4.6. Why is it your sample mean? It's because of how it's worded, right? So we have a random sample of 20 children. So now we have n equals 20 from the city, from this small city, I guess. And that sample has a mean of 4.6 and a standard deviation of 2.2, right? And so that's what makes it the sample mean and the sample standard deviation. So S is 2.2. There are units, years, right? But I usually just kind of drop it. And that's fine. Okay. So the type, let's start there. The type of question is a one sample mean question. All right. Which means that this is the part of the formula sheet that we're restricted to. These are our only options. All right. So what we're asked to do is we're going to evaluate Georgiana's claim or that the opposite might be true using a hypothesis test. And so we're going to do a hypothesis test, and it's worded a little bit strangely because they want to do a two-sided hypothesis test. Okay, so Georgiana claims that in a small city renowned for its music school, the average child takes less than 5 years of piano lessons. We can actually do the one-sided hypothesis test. The reason that they're forcing it to be, or the opposite, is because they skipped one-sided hypothesis testing, right? But it makes it weird for a lot of these questions. So I'm actually gonna just scratch this. Right. We have the tools to see if a child takes less than 5 years of piano. So this is the value that I want to compare my sample mean of 4.6 to, right? And so right away, I know that my mu naught is 5. Let's start with the conditions. Like I said, what's nice about means questions, one sample means questions, is the conditions are the same if you're doing a hypothesis test or a confidence interval. In this case, we're doing both, right? So if this was a proportion question, you'd have to check all the conditions, right? And so a little bit easier. The first condition is independence. We were told that the children were randomly sampled, so we can assume that they're independent of each other, even though it's from a small city, right? That's totally fine because we want to only talk about this small city, right? So that's our population. So the sample was randomly selected. So we may assume the children are independent of each other. The second condition is the normality condition. We don't have a lot to go off of here. I know the sample size is less than 30. So what do I have to argue? I have to check if there are any outliers. We're not given any information. I don't have the data. I can't make a histogram. I can't even look at it. I don't have the minimum and the maximum. I don't have the mean and the median. I have the mean, I don't have the median, right? And so I don't have a lot of options. My hands are tied. I have to assume that there are no outliers, right? Fine. Usually that's just what we do anyways. Okay, and so since n is less than 30, we assume, and I'll underline that assume because usually that's kind of sticky in the beginning, right? Are we allowed to do that? Yes, we are, right? We have to. We assume the distribution is approximately normal. Okay. So now I'm ready to do part A. And maybe I'll grab it so it's clean instead here. So we have to do a hypothesis test. And let's see here. I'll do that because what I want to do is just show you how to set up the hypothesis if we wanted to do that version. And maybe I'll use a different color here. But Georgiana's claim was that in a small city renowned for its music school, the average child takes less than 5 years of piano, right? And so the null hypothesis is that the population average amount of time that the children take piano mu is equal to 5 years. Right? What she suspects is that mu is actually less than 5, right? She claims that the average amount of time that they take is less than 5. 4.6 is less than 5. We just want to know if it's significantly less than 5. Right? That's what we're testing. So this is a one-sided test versus if we wanted to test the original question, right? Then the null hypothesis would be that mu is equal to 5. And the alternative is that mu is not equal to 5, right? A two-sided test. But that's because they made the one-sided tests optional. Part of the reason they did that is because we should always do two-sided tests, but sometimes the questions kind of lend themselves to checking if it's less than 5 or right. There's kind of good reason. The only difference between these two are going to be the p-value, right? Here you have a two-sided p-value and here you have a one-sided p-value. But besides that, and then that might influence your conclusion, right? But besides that, the procedure stays the same. Oh, and I guess this is step, I should stick to my steps. State the hypotheses. The steps all stay the same. We're going to get a p-value. Your conclusion stays the same and it's based off of the p-value again, right? And so everything kind of stays the same. Step 2, do the test. Which, if you're bored, you can call it calculate the test statistic. The null hypothesis, the test statistic, they're on your formula sheet, right? So kind of a default null and alternative hypothesis, and then T is your test statistic, which is why we call it a t-test, right? So that's what I was saying. Oh yeah, if you're kind of spitballing ideas, how are we going to analyze this? You just kind of make sure you have numerical data. Oh, couldn't we do a t-test? There's lots of different t-tests, right? But it's a safe bet. And people are always sold. X bar minus mu naught over S divided by root n. We have all these components from the question. So T is equal to 4.6. How far is it from 5? If the spread of these data is 2 divided by the square root of 20. Now I kind of skipped around here. I have T is negative 0.4 divided by, and I have 0.49193, oops, 34955. So T is negative 0.8131156,282. Just as before, to match the table, right, you can have a glance at the table and notice that it's 3 decimal places. So you're going to need at least 3 decimal places, right? And if you want to play it safe, go to 4. But T is negative 0.813. to 3 decimal places. Right? 4 if you want to get snazzy. Yeah. That's not very far. So step 3. Find the p-value. In order to find that p-value, you need the degrees of freedom, which is n-1. And this one, although it really hurts me, I do usually calculate across the page. Otherwise, it would take 3 lines. That's crazy. I know, I'm totally compulsive with stacking my equal signs. So it really, really hurts me. But now I have 19 degrees of freedom. And hey, I just made that basically the same here. I'm just gonna grab the 19 section because we just need the p-value for now. Didn't grab it. I'm sure you've already found the area already. There. So I have 19 degrees of freedom. And my t, right? I'm looking for the absolute value of t equal to negative 0.813 is going to be between 2 values, right? 8.13, somewhere here, 0.688 and 0.861. So then the one-sided p-value, and this is what would change if you were to do the 2-sided test, right, is going to be between 0.20 and 0.25, right? Versus the 2-sided p-value is between twice that, 0.4 and 0.5. Either way, your conclusion is the same. Right? It's harder to reject H0 for a 2-sided test, and that's why it should be your default. But I'll let you write the conclusion and we'll pick up there on Thursday. If you have any questions, let me know. But we'll also do the confidence interval and it'll be great. Stop this.